All right, guys, it's me, obviously. Welcome back, I guess. I'll miss seeing you guys this week. I'll see you on Thursday, and as I ended up catching the COVID, so I gotta stay home for a couple days. It's not too bad. Blocked nose feels like a cold, makes you pretty sleepy. Other than that, just like having a cold, so um, no worries. But even though I'm sick, I'm gonna teach you guys some chemistry. So today we're going to talk about something called the mole, and I have a homework assignment posted for you for you to do after watching this discussion. It's on the class page. I'm sure that you can either get a Chromebook or um, I will also send a copy up with the lovely and talented Mrs. Koch to make photocopies and provide to you of the worksheet, and you'll be able to do it. So we spend some time learning how to name chemical compounds, and hopefully you don't forget that because as we move through the course of this school year, I'm going to be referring to chemical compounds by their names, and it becomes particularly important when we start balancing equations and just talking about chemistry. And you need to become conversant in the language of chemistry if you want to succeed, if you want to move on and maybe take up chemistry in the future. So, the next topic on our big list of chemistry hits is the mole. Now, I want you to think for a minute about a contest. A contest where you have a big 5-gallon water jug, those big ones that sit on top of a water cooler, and it's empty. And let's say uh, you see one that's entirely full of pennies from the bottom to the top. It's full of pennies. And there's a sign on it that says, guess how many pennies in this jug, and you'll win the prize. You're thinking, wow, if I can only get my hands on that jug full of pennies, I could count them all. But 5 gallons worth of pennies is a tremendous amount of counting to do. You probably wouldn't want to do that. But what could you do? Could you maybe take a handful of pennies that you can count, maybe 100 of them, and weigh the 100 pennies and write that down, and then weigh the big jug full of pennies, put the 100 pennies back in, weigh the big jug full of pennies, subtract out the weight of the empty jug, and then if you know how many grams there are in 100 pennies, and you know the total number of grams of pennies in the jug, you could figure out how many pennies were in there. It's a very trivial exercise. Well, that's the same thing in the concept of a mole. The uh, the mole is nothing more than a chemist's unit for saying, hey, I've got this big ton of molecules, but I can't count them all because they're too tiny. But I can weigh them and or get the mass of them, and by doing so, I can figure out how many molecules I have. You might think, well, why is that so important? Because when you do chemical reactions, we do chemical reactions and we base it upon something called stoichiometry, which we're going to learn here in the not too distant future. But molecules act like discrete particles. So if this molecule A and molecule B are coming together, they need to bang into each other with a certain amount of energy to cause a chemical reaction, and then something might happen. And so when we think about chemicals reacting, we have to think about numbers of chemicals coming together, not grams. But when we go ahead and try to count these um, molecules, it's a difficult task because they're so tiny. So we have this idea of the mole. Now the mole is like a dozen, 12 eggs in a dozen, 2 dozen, 24 eggs, whatever, or a gross, 144 things in a gross. You might also have a ream, that's 500 sheets in a ream of copy paper. So how many in a mole? How many things in a mole? Whoa, it's huge. This mole to the minus 1 means per mole. So there are 6.022 times 10 to the 23 things per mole. 10 to the 23. That's an unbelievably, unimaginably large number. And that number is called Avogadro's number. And like I said, I'll be following this up with a little video cartoon about Avogadro. I think you'll enjoy it. And that's how many things there are in a mole. So if I have a mole of carbon atoms, I get that many carbon atoms. If I have a mole of hydrogen atoms, I get that many hydrogen atoms, etc. Okay, so here we go. How do we know how many grams there are in 1 mole of something? Well, we have our friend the periodic table. The periodic table tells us how many grams there are in a mole. All you have to do is look at it. Um, for example, you're sitting in the room now. Look at the periodic table on the wall or pull yours out. Look at carbon. And somewhere by carbon it says 12.011. It says 12.011. Well, that's how many grams there are in a mole of carbon. If you go and look at copper, you see that it says probably 63.45. If you look at zinc, it's 65 point something. That's how many grams there are in a mole of those particular things. Now, you might be saying, well, they're the same number of particles. Why don't they weigh the same? Well, don't forget, I mean, atoms have different numbers of protons and neutrons in the nucleus, and some are very large and some are very tiny. Think of it this way. If you had a dozen bowling balls or a dozen eggs, which would weigh more? Well, unless you had unusually large chickens, the uh, the bowling balls should weigh more, the dozen bowling balls. So it's the same thing with these atoms. So chloride uh, ions, 1 mole, 35.45 grams. That comes from the periodic table. And you might say, hey, Koch, chloride, doesn't that have an extra electron? Shouldn't that weigh a little bit more than what it says on the table? That would be a good question, but electrons compared to the nucleus of the atom practically weigh nothing. Um, an electron is 1,800 times less massive than a proton. So gain an electron, lose an electron, it doesn't really affect the mass of an atom or an ion. It's kind of like standing on a bathroom scale, weighing yourself, and then you know taking 2 pennies out of your pocket and standing on the bathroom scale and weighing yourself again. It's not going to even register. Electrons are tiny, tiny, tiny. So, what if I have a chemical compound? It's easy. All we have to do, first of all, don't look at this stuff right yet. Don't look at that stuff yet. Just look at the chemical compound. Chemical compound says CO2. It means I have 1 carbon and 2 oxygens. So if I go to the periodic table and I look up the value for carbon, it says 12.01. If I look up the value for oxygen, it says 16. I've got 2 of them. 16 times 2 is 32, plus 12.01. I add that together and I get 44.01 grams per mole. You might be saying, hey, well, what's this deal with AMU? What are they talking about with AMU? It's like Limu Emu or something. But what the AMU stands for is atomic mass units, and atomic mass units and grams are related mathematically. And it's not something we need to go into here, but if we're talking about 1 carbon atom, that has an atomic mass of 12.01 atomic mass units. But if I translate that to grams, that tells me also how many grams in a mole. We will not be dealing in the realm of atomic mass units. We're going straight into grams per mole. That's going to be our important thing here. So when you look at that number on the periodic table, understand it means grams per mole. So 1 mole of carbon dioxide molecules, CO2, is 6.022 times 10 to the 23rd carbon dioxide molecules, and it has a mass of 44.01 grams. Now you should be able to go to any chemical compound that I give you and look at the periodic table and calculate how many grams in a mole. Now, boy, this is weird looking at myself on the computer. If I do this, I look like I'm really weird looking. Anyway, bear with me. We'll get through this week together. So how's that going to help us? Well, in chemistry, we're going to go into the laboratory and we're going to mass out or weigh out a certain number of grams of something. And we have to figure out how many moles we have. On the other side of the coin, we might need a certain number of moles of something, so we better darn well know how to get the number of grams of that stuff. So we need to convert back and forth. So this says, how many moles of sodium chloride are there in 48 grams of sodium chloride? Well, NaCl, if you go to the periodic table, Na is roughly 23 grams per mole, 22.98 or something like that. And chloride is about 35.45. So I've got one of each, one sodium, one chloride. So I add them up and it's approximately 58 grams in a mole. So you set up a conversion, 48 grams times 1 mole per every 58.44 grams. And that's going to give us our number of moles. 0.082 moles of sodium chloride. Nothing to it. I mean, this is very basic stuff. Now, if I give you moles and I want to know grams, you just go the other way around. You still have to get the molar mass of this stuff, and it's C2H6. And by the way, we call that molar mass. And C2H6, I go to the periodic table. I'd see 2 carbons, each approximately 12, 6 hydrogens, approximately 6 times 1 are about 6. So 24 plus 6, around 30 grams in a mole of C2H6. So I want to get from moles to grams. So I start out with the number of moles, and I know I have to put the number of grams in the numerator and the number of moles in the denominator. And I multiply across the top. The moles cancel. And you get 562 grams in 18.7 moles. Okay, this doesn't take a rocket scientist to get these things down. It just takes some practice, which you're going to be doing. Now, this is where things get a little bit more interesting, I think. It says converting from grams to molecules. Well, in order to go from grams to molecules, this question says how many water molecules are contained within a 56 gram sample of water? Well, we have to convert from grams to moles, first of all. And I do that. I go to the periodic table and I calculate the molar mass for water. 2 times hydrogen plus 16 for oxygen is about 18.02 grams per mole. And I put the grams on the bottom because I want to get to moles. And then I go ahead and I say, well, I get 6.02 times 10 to the 23 molecules per mole. And when I do the math, I find out, whoa, I get 1.9 times 10 to the 24 molecules of H2O. I could take this one step further. I could say, well, how many hydrogen atoms are there in 56 grams? Well, we know we have 2 hydrogen atoms for every 1 molecule, so we just multiply by 2. How many hydrogen atoms are contained within a 56 gram sample of water? Nothing to it. Got our 56 grams. 1 mole is 18.02 grams. We multiply by 6.02 times 10 to the 23rd molecules per mole of H2O. And then we get 2 hydrogens. So right here, we're going to have 2 hydrogens per every 1 molecule. Oh, this is terrible. I can't write with a mouse. Oh my goodness gracious. Of H. This is horrible. H2O. Never mind. Get out of there. Go away. Let me have them do it. 2 atoms of hydrogen per every 1 atom one molecule of H2O. So you come up with a number of 3.7 times 10 to the 24 atoms. All right, so I'm going to post this, and I'm going to ask the sub to show it to you. Pay attention to it. It's going to be on the class page. It's on the YouTube channel. So smash that like button and subscribe, and you'll get all the chemistry videos and maybe some cooking videos too that you can stand. So it's Dr. Koch signing out until tomorrow. Take care and have a good day.